Okay, so coming up, we have exam 4. That's a week from today. So the night class is taking it Monday, 4/28, and the day class is Tuesday, 4/29. And the topics are going to be simple circuits. I think those practice problems might be called Ohm's current and Ohm's law, maybe. So but it's just simple circuits problems. And then regular circuits, more complicated circuits. And then the first part of electricity and magnetism. So that's the stuff that we're doing right now, and we'll finish this today. So yeah, this is going to include the magnetic field that's produced by a current in a straight wire. The magnetic field produced by current in a coil of wire. We've talked about both of those. And then the last one that we're going to get to today is the force produced by a magnetic field on a current passing through it. So the current passes through the magnetic field, and the magnetic field applies a force. So when we start talking about how currents are produced by magnetic fields, that's the stuff that's not going to be on the exam. Any questions about the test? And then we'll have one more problem set. That'll be posted soon. And it'll be due by the end of finals week. So you'll have plenty of time to work on it. We're not going to meet and talk about it. You're just going to turn it in. So I believe that your final is on Tuesday this year. So Monday is the first day of finals week. Yours is on Tuesday. So everything's done pretty early, but if you want to wait until Friday to turn this in, that's fine. Okay. And it's going to have some of that stuff. Remember, in the last thing you had to turn in last semester, I had you do like an outline of the topics we've covered. There's going to be something like that, just like reminding yourself what everything is. One thing I was thinking about the other day is like, what if I let you rewrite like all the equations and gave like all the quantities just like new names? So now like what if the current was called omega, and just make you think about like what's what in the equations, not just like, you know what I mean? I don't know, maybe that's a stupid idea, but I was thinking about that on my bike ride home. But something like that, outlines, that kind of stuff, just try to get all the juices flowing. And then labs. There's a lab this week. Next week, they're makeup labs only. And if you'd like to come and ask questions, especially if you want to come to the lab on Monday, like before the test, feel free. But otherwise, you don't have to come. And then the last week of classes, there's a lab, and that's the week that you'll be doing the makeup exams in class. So this week and the last week are the last two labs. Any questions about any of the stuff that's coming up? Yeah, right. So I'll just bring versions of all of them in, and you can tell me which one you want. They'll all have quizzes on them, but I'm not going to like mix and match the quizzes. So that's just too much bookkeeping. So you can't take quiz 1 and exam 3 or something, but you can take like if you think like, wow, I've got perfect scores on all my tests, but I did get one wrong on one lecture quiz. You could take the lecture quiz to get your point back, because I know that would be killing you. And then, so you can retake a lecture quiz, that's all I'm saying. But you have to do the same one that you retake the exam. Any questions about anything? Okay. So now we'll get back into the last topic that's going to be on the exam next week. That's the third application of the right-hand rule. And that is the force produced by a magnetic field on a current passing through that magnetic field. Force is a vector. And so we're going to split this up again into a way of calculating the magnitude of the force and a way to calculate the direction. The magnitude is calculated this way. Force is equal to the current times the length L times the strength of the magnetic field times the sine of an angle theta. I'll tell you what all these mean in detail. So I is the current passing through the magnetic field. L is the length of wire exposed to that magnetic field. B is the magnitude of the magnetic field vector and theta, if you put the current and the magnetic field vector B tail to tail, that's the angle between them. And it's important that you use the smallest angle between them. So if you have a current going this way and a magnetic field going this way, okay, you'd put them tail to tail like this. Now there are two ways you can measure this angle, right? You could measure all the way around the long way. That's going to be close to 270 degrees in what I've drawn. Or you can measure the short way. You have to always take the short way. Okay? Otherwise you'll get negatives and stuff. Okay. And one thing to notice about this angle, because this is maybe a little bit of a surprise, you would think maybe, and in a lot of physics calculations, it works this way. How would you get the, like what directions would I and B have to be for the force to be maximum? You might think parallel, like in the same direction. It's actually the opposite of what you would think in this case, because if they're parallel, what's the angle between them? 0. And what's the sign of 0? Right. If they're perpendicular, you'd think maybe they have the least to do with each other. But if they're perpendicular, what's the angle between them? 90. And what's the sign of 90? 1. And that's the biggest sign can be. So notice F is maximum when I and B are perpendicular, and minimum when they're parallel. Weird? I don't know. It might be. But that's how it is. Yeah, in both, that's right. In both cases, it's 0. Yep. Any questions about that? So that's the magnitude. And we'll do some example problems. And now the direction, which is usually the tricky part with this stuff. The direction is going to depend on the third application of the right-hand rule. And the way this works is imagine, so this is sort of a side view of a circle. Imagine the current is going this way, and the magnetic field vector is going this way, okay? So that's the current, that's the magnetic field vector. Think about the circular path that I would have to take to align with B, okay? So I've already drawn the circle. It's sort of this disk here. Okay. So think of the circular path I would have to take to align with B. Again, you have to use the shortest path or else you come up with the opposite answer. That circle is represented by your fingers. And then your thumb is in the direction of the force. Okay, so in this case, to start with I and align it with B, you have to go in a circular path like that. And so the thumb is pointing up. And so the force vector is up. One way that I think, especially when you're first trying to make sense out of this, one way to do it is to take, two pencils or something and think of, so if you have the current going this way and the magnetic field going this way, and just think about the motion, like actually take the current and move it through the motion to line it up with B, okay? So in this case that I have drawn, that is a circle like this, okay? Then your fingers represent that circle, and your thumb gives you the direction of the force. And here's something else weird. Notice that the force is perpendicular to both the current direction and the magnetic field vector. That's using, this is all based on a mathematical way of multiplying vectors called the cross product, and that's a property of the cross product. Okay, let's do a calculation. So let's start with one where we know the value of the magnetic field vectors. So say that they're pointing to the right with a magnitude of 0.1 Tesla. Okay. And let's say that the current direction is, so there's the wire. And let's say that the current is 20 amps, okay? And let's say that the amount of wire that's exposed to that magnetic field is 0.5 meters, okay? What's the force vector applied to the current? Well, the force to come up with the magnitude is equal to the magnitude of the current, so 20, times the length of the current that's exposed to that magnetic field. That's 0.5 meters. Times the magnitude of the magnetic field. That's 0.1. And what's the angle between the magnetic field and the current? 90. So sine of 90, that's 1. So, you know, that just cancels out. And you end up with 20 times 0.5 times 0.1 is just 1.0 newtons. And now for the direction, which way do you have to rotate the current to make it align with the magnetic field? So if this is the current and this is the magnetic field, you have to rotate the current this way so the force is out of the board. Okay? So you have to just picture the circle that you're sweeping out by, so put them tail to tail, sweep out a part of a circle to get I to line up with B. So that circle is counterclockwise. So if your fingers go counterclockwise, your thumb's coming out of the board.
So when I wrote my vector, I put 0.1 Tesla over 0, because we have x and y. Or it would be
Oh, okay.
negative. Would it be appropriate to put a third direction?
Yes, it would be appropriate, but you don't have to do that, and it makes it, that's more than I expect you to do, but yes, it would be appropriate. And so the right-hand rule, so if I is this way, B is this way, your fingers are like that, and so the force vector is out. So there's the answer. Any questions about that?
Would it be positive?
So if you had a coordinate system, yeah. If you had a coordinate system like this, positive z would be out, yes. Yep, so it would be 0, 0, 1. All right, so now let's do a calculation related to that. Remember that smoking contraption that I brought in here last time? So the demo that I brought in last time, the way it worked is you had two wires that were parallel like this, and there was a current going the same direction in both of these. Just to illustrate a point in a second, I'm going to make these two different currents. They were actually the same current, but and they were huge currents, which is why they made the insulation smoke. So 200 amps here, let's call this one 100 amps. Okay, and let's say that the total distance was 0.8 meters. Did the currents make the wires attract each other or repel each other? Anyone happen to remember? Yeah, it sucked them together, okay? And so now we have the ability to calculate why that is. and even how strong the force is between them. So let's say also that there was a distance between them of 10 centimeters, so 0.1 meters between them. Anybody have like a strategy for calculating the force of attraction? So essentially our idea is we're going to choose one of these to be our chosen object, and we're going to calculate the force on that chosen object. Anybody have an overall strategy for how to come up with the magnitude of attraction of force? Yeah, we're going to get to that eventually. But so I guess the first thing I want to get at is, like, notice in this example, I gave you a magnetic field, and we calculated the force on the magnetic field. I'm not giving you a magnetic field this time, right? So is it even the same thing? Well, it is the same thing, because once we choose the one that we're going to isolate, say that we choose to isolate the 100 amps, then sort of the first calculation we have to do is calculate what the magnetic field is at the location of this wire that's produced by the other wire. Okay? So we're going to use, if we choose arbitrarily to isolate the 100 amp current, that's going to be our chosen object. We're going to use that 200 amp current to calculate a magnetic field at locations 0.1 meters away. Then once we know that and we figured out the direction, then we can move on to the problem like we just did. Okay, so it's sort of two steps. It gets confusing though, because now you have, like in this one, you don't even have to think about it. Like, what magnetic field are we going to use? Oh, the only magnetic field that's there. What current are we going to use? The only current that's there. Now you can't do that, you know? So now you have to think about which one of these is producing the magnetic field, which one is producing the current that matters, okay? So we're going to do it two ways. So what we saw was that they attracted each other. We're going to first calculate the force applied to the 100 amp current. And second, we're going to calculate the force applied to the 200 amp current. If they attracted each other, what's going to be the force direction on the 100 amp current? Toward the 200, yep. And what's going to be the force direction applied to the 200 amp current? The opposite direction, toward the 100. And what do we expect to see about the magnitudes of those forces? Which one's going to be stronger? Well, so that was sort of like a mean way to ask it, because so it's gonna obey Newton's third law. I mean, the fact is, this one is going to apply a force pulling towards that. This one's going to apply an equal and opposite force pulling that way. Okay, one's applying a force to the other one's applying a force to it. So Newton's third law says they have to be equal and opposite.
But one produces a difference.
No, it's going to be the same force, and you'll see why as we go. But the reason is that if you came up with a single equation that took you through both steps, you'd see that both currents end up multiplied into that. So one's going to produce a bigger magnetic field, one's going to produce a smaller magnetic field, but then the opposite one is going to be multiplied by a bigger current when you calculate the force, and that's how it works out. All right. So what direction are the field lines? So we're doing part A. So the first step is calculate the magnetic field vectors produced by the 200 amp current. All right, well, the magnitude is equal to 4 pi times 10 to the minus 7 times the current of 200 amps divided by 2 pi, and we need a R. What's our R value going to be? 0.1, yep. So what we're doing right now is calculating the strength of the magnetic field at a fixed distance from this. And the distance we want is, we want it to be, so at any fixed distance from this, we're going to have circles around it, right? We want the distance where the circle hits that wire. So we're going to calculate the magnitude of the magnetic field, 0.1 meters from the 200 amp current. All right, so you get 2 times 10 to the minus 7 times 200 divided by 0.1. So that is 4,000 times 10 to the minus 7, which is 4.0 times 10 to the minus 4, right? And now we need to use the right-hand rule to figure out what the direction of that magnetic field vector is. What direction do the field lines, so remember the field lines about a straight wire are circles around the wire. What direction, what circular direction do those field lines go around the 200 amp wire? Your thumb goes in the direction of the current. So the circles are out the front, in the back, like this. And so on this side of the 200 amp wire, the magnetic field vectors are pointing into the board. And on this side, they're pointing out of the board. Anyone confused about that? Okay, so here's the current direction. So put your thumb in that direction. And yikes. Okay, so you're looking at like the back of your hand. And so those field lines are going this way. And now to come up with the vector directions, at every point, the magnetic field vector has to be tangent to this circle. So tangent to it over on this side is going into the board. And tangent over here is coming out of the board. And if we wanted it right in front, it would be going this way. The place where we care about it is over here. And so right-hand rule 1 says the direction is out. Okay, so now we can go on to calculating the force. We have a current of 100 amps that way. A magnetic field, if you put them tail to tail, magnetic field comes out of the board with a magnitude of 4 times 10 to the minus 4 Tesla. The magnitude of the force is equal to the current times the length that that current's exposed to the magnetic field. What's that? That's the 0.8, yep. Times the magnetic field strength, 4 times 10 to the minus 4, times the sine of the angle between them. What's the angle between them? 90. The majority of problems are going to have angles of 90 because it's more interesting. You get, you know, bigger forces and stuff. And so you get a value of 320 times 10 to the minus 4. So 3.2 times 10 to the minus 2 newtons, or 0.032 newtons. So it's not really that strong a force, but it doesn't take much force to make those loose wires suck towards each other. But now we have to figure out the direction. So which way do you have to rotate the current to make it line up with the magnetic field? And notice if you try to make the magnetic field line up with the current, you get your direction backwards. So if the current's going down and the magnetic field is coming out, to make I align with B, you have to rotate that way. So we're talking about a circle in this direction. So your fingers do that, and the force direction is to the left, which is towards the other wire. So this is the direction to make I align with B, and so this is the force direction. So it's toward the other wire. Anyone have any questions about that? Okay, so now for part B, why don't you work on this one? It's, you know, sort of the same steps, but you're going to use different numbers in different places, and the directions are going to be different. So work through it, talk to each other, and let me know if you have questions.